Hey guys, welcome to Safi Max. In this video, I will continue from the point where I ended the video statistical interpretation of wave function as part 1 and would rewrite the final equation of that video, that is equation 7, which is this form of the equation. We can put this equation into a more simplified and meaningful form by defining two other quantities, the probability density and current density, in the following ways. That is, if we define the probability density P as the product of psi steric psi and the current density J as iota times h bar divided by 2m multiplied with psi steric partial psi over partial x minus psi partial psi steric partial x. Replacing this definition in equation 7 leads to partial p over partial t equals partial j over partial x, or I can rewrite the equation into this form by bringing partial j over partial x to the left side of the equation. This equation is identical to the continuity equation of fluid dynamics given by partial rho over partial t equals partial j over partial x equals 0, where rho represent the number of particles per unit volume and J the current density of fluid. Analogically, in equation 7, we may associate P equals psi steric psi equals absolute square of psi with position probability density in the sense that P times d of x equals absolute square of psi times d of x will be proportional to the probability of finding the particles in a differential length element between x and x plus dx. This meaning given to the wave function is in fact the so-called Bohren statistical interpretation of wave function. In this view, it seems at this point that the wave function itself does not make a direct confrontation with the experimental measurements of position of a particle, but does only through the absolute square of the wave function. So in the case of continuous probability distribution, the probability of finding the particle in certain length element between 2 points A and B can be expressed in the form of, that is, the probability of finding the particle between points A and B equals the integral between A and B of the probability density capital PAB times dx, which in turn can be expressed as the integral from A to B, the absolute square of psi of x times dx. Since the particle must be somewhere in the region, therefore, according to normalization condition of probability, that equation for the whole region can be expressed in the form the probability of finding the particle in the whole region, that is, the probability from minus infinity to plus infinity equals the integral of the probability density from minus infinity to plus infinity, which in turn can be expressed as the integral of the modulus square of wave function from minus infinity to plus infinity, and that must be equal to 1. This normalization condition of the probability density is used to normalize the wave functions for particles obtained from the solution of Schrodinger wave equation. Remember, not all solutions obey this condition. For example, the plane wave solutions to Schrodinger wave equation do not obey this condition. Now let us observe that what happens to the probability of finding a particle in the whole space with the passage of time. If we differentiate this equation with respect to time, we can write the probability for the whole space equals the derivative of the integral of probability density over the whole space, which can in turn be written as the derivative of the integral of the modulus square of the wave function over the whole space equals the derivative of 1, which of course equal to 0. This means that the probability of finding the particle in the whole space is independent of time. This must be so because it is 100% sure that the particle must be somewhere in the whole space.